Okay, so today we're going to do a review of some mathematics. Oh, I have feedback.
What is that noise?
Okay, that's now gone. I think what it does, there is a slider here that plays back, I think, what I record or something. Anyway, the topic today is math, really. Chapters 26 and 27 in Variance book are an excellent resource, and I'm going to go over those, at least point out highlights, after I go over the one item I meant to upload for last Tuesday and I didn't, which is the handout you have now. For those who are going to watch this on video, I printed out for everybody and I'll bring it on Tuesday. The slides I just uploaded on Canvas on linear independence. So I will go over those a little bit now, and then we'll take it from there. And I aim to cover pretty much everything in chapters 26 and 27 in Varian, only by pointing out the more important things. Okay, so before that, is there a question you have from the math review in class on Tuesday? No questions? No? Okay. So let's look then at this handout. And by the way it prints, you start at the left, you go right, and then down. Okay? So let's start with a vector and its scalar multiples. As always, I am going to illustrate this in a two-dimensional space. So suppose I have a vector. By convention, we put the vectors based at the origin, and the coordinates tell us where to put the endpoint. So this vector v would have coordinates v1 and v2, and this is the origin at 0, 0, 0. Now, what does it mean to multiply a vector by a scalar? And I mean in terms of the picture. So, as you might expect, if I want now to multiply by 2, then the vector cannot stay where it is. What should happen to it, according even to your high school math class or physics probably, is it should become twice as lengthy and stay in the same direction, and so on. So by choice of the number to put to multiply the vector with, I can generate any point, well, by point and vector, I mean more or less the same thing in terms of location here, right? So a vector, since we agree to put the base of the vector at the origin, there is a one-to-one correspondence between a vector and a location of specific point. So oftentimes I will jump and say the point instead of vector, vector instead of point, and it really means the same thing. Although multiplying a point by a number doesn't really mean anything, that's okay, to understand, I meant to say vector. Okay, so let's extend the whole line. The vector v we started with is on, right? That line, to the extent I draw it okay, which is okay, doesn't look very straight. What can you do here? You can generate every other vector or point in this line by choosing what number to multiply v with, right? So if you want to make it go down here, you have to multiply v by a negative number, okay? So that is on the fourth on slide down here. definition of let n be a positive integer, let v in Rn be a non-zero vector. The line generated or spanned by v is the set defined as I show here. That is what I just said on the board, right? But the script L of v is the formal notation. It is the set of all points or vectors Rv, where R is some real number. Okay? So, this line is the LV of that slide. All of it. All of the line. So, okay. So we can say, if you start with a vector, it manages to generate an entire line, but not more. And also, you need to start with a vector that's not the zero vector. Because if you start with a zero vector, no matter what you multiply it with, you're going to generate nothing except that point, the origin. So that already has a little bit of the idea of linear independence. As we will see now when I finally define it properly, a set of one vector is linearly dependent if the vector is zero. But the general definition for multiple vectors is much more interesting. And to motivate that, let's think about what can we do by taking two vectors to start with. And so each one is going to generate a line by this process. But we could also add vectors, right? And so we can say, suppose I have this vector v and some other vector, oh, let's call it w, over there. All right? What can I do with these two vectors if I allow myself to have different real numbers multiplying v1 and v2? What I can generate actually is the entire two-dimensional space. So this is L of w, but all of the space is L of v and w together. That is, on the bottom of this page, the linear combination is defined, right? I used v and w instead of v1 and v2, but I'm talking about the same thing. How can I, you ask, generate any point in the whole plane here? Well, okay, here's a point, right? Here's a point, and I ask, I come in. I ask, how can I get this point? How can I get this point? By multiplying the v and the w by an appropriate number and then adding the result. Here's how you find out. You think more or less as these lines as the new axes for your system. So you say, okay, go to this point you want, any arbitrary point, and draw a parallel line. Now it's not writing. Okay. Let me grab another one. So go to the point you want and draw a line parallel to one of the lines generated by these vectors, and then do the same for the other line. You can always do that, right? You have the lines, you have a point, go to that point. From the basic axioms of Euclidean geometry, from a point outside of a line, you can draw exactly one line parallel to any given line, right? Now, look where these dotted lines hit. L of w and L of v, right? So then you realize if you multiply v by whatever it takes to make it go here, and you multiply w by whatever it takes, there will be negative numbers in both cases, to go here, right? So then the sum of this vector and that vector is the vector you wanted, right? So you can do this for any point. So these two vectors v and w generate the entire plane, or span the entire plane. Is it clear for everybody? I took this point completely arbitrarily. I could do it anywhere, right? Okay. So that then indicates what you can achieve if you start with two vectors and finding their linear combinations. But now, are we sure we're going to get the whole plane? Notice that I chose v and w in a particular way, namely, they're not on the same line. If they happen to be on the same line, then I cannot do what I just said. So for example, let's redo new picture. Suppose I have a vector v1 and a vector v2, which are exactly on the same line. I don't care if they point in the northeast or southwest direction, but they're on the same line. That matters. So if I extend the line, this then is L of v1, and at the same time L of v2, right? And at the same time L of v1, comma v2. I cannot possibly generate points outside the line by making combinations, linear combinations of v1 and v2, right? Because anything I do by multiplying v1 and v2 will give me a point in the line and not outside, right? So what I said earlier, where I showed you v and w, and I said, oh, you can generate any point in the plane. Well, it's not true if that's the case. This is the case where, in fact, the two vectors do not really convey independent information. They convey information that if you have one vector, you can get the same information as if you had the other. By information here, I mean instructions for building a whole set of points. Right? Each one gives you instructions for building a line, and if they are on the same line, their instructions are redundant. They say the same thing, build this line. Right? But if they are not on the same line, the instructions, as in the previous picture, cover the entire two-dimensional plane. Okay? So that gives us the concept, the idea of the need for linearly independent vectors. Right? By the way, we talked in class about vectors. We talked about the equation systems, and equation systems where we really did not have, say, two equations, but it was only one. I gave an example on the board where one equation was a multiple of the other. That's the same idea, right? The coefficients of each equation, the coefficients of the unknowns, are vectors, and they convey a certain amount of information, right? So so when you have, for example, okay, I had like 2x1 plus 3x2 is 5. I think I might have had exactly that actually. And 4x1 plus 6x2 is 10, right? So you can think of these vectors also, the columns, right? So what does it look like? Well, I have, this first equation is the 2, 3 times x1, x2 equals 5. Oops. Let's put it all. 4, 6, and then 5 and 10. Right? So what this multiplication does, right, is it creates a point from these two, from this vector, and a point from that vector, right? But it's based on the same vector. So it's not going to give you additional information. So that's why we need the concept of independent vectors, and this is one hint of how it relates to linear equation systems. So now let us define independence of vectors. Okay, so I have linear dependence defined. It's in the third piece of paper, top left. Let's read the definition. Let n be a positive integer. Well, right. All of these definitions work for any dimension space. The only reason is I keep n equals 2 here is I can make you a picture. Okay, but the definitions are perfectly good for any dimension. Okay, so suppose that you have v1 and v2, two vectors in Rn. The vectors v1 and v2 are linearly dependent if there exist real numbers c1 and c2, not both of them equal to 0, such that c1 v1 plus c2 v2 is 0. Let's understand this. What does it say? First of all, given the equation in this definition, you see why c1 and c2 could not be 0 at the same time, because if we allowed that, then the definition is trivial, right? So we don't allow both c1 and c2 to be 0. So we say that if that's the case, that's the definition of linear dependent set of vectors, and linear independent is where this definition is negated. Okay? So, in this case, how can I see that these two are linearly dependent? Well, I could measure the length of this, measure the length of that. Suppose the length of this is 1, for the sake of argument, or I define it to be 1. And suppose this, well, it looks like it might be 1/2, right? And half that length. For the sake of argument, let's say that's it. So I can then say 1 times v1 plus 1/2 of v2 is the 0 vector. Backwards. If I have this and add it to that, they cancel each other out and you end up at the origin. Okay? Okay, so then I have found my numbers. Let me rewrite it so it's actually readable on the video. 1/2 v1 plus 1 v2 is the 0 vector. By the way, I did not indicate here the 0 is a vector, but since we have vectors on the left-hand side, it is understood, I hope, that what I have on the right-hand side is a vector of the same dimension, otherwise my equation doesn't even make sense. So, you see I have my C1 and I have my C2 of the definition. C1 is 1/2, C2 is 1, they are not both 0. So the definition is verified. So these two vectors are linearly dependent. Okay? Could I do it if they were not on the same line in R2 still? Well, no, I can't. Let me illustrate that. Let me delete this. try to keep the axis, however. I have to draw them again and again. Okay. So here's V1, and let's say here's V2. They're not on the same line this time, okay? Now, I can multiply V1 by any number, and I will then generate this space. And with V2, as we said before, I can generate this space. Now, however, can I, by multiplying by the appropriate R1 and R2, or C1 and C2, can I get the sum of C1V1 and C2V2 to be the zero vector? You can actually try, choose some actual numbers and try, and it is not possible unless C1 is 0 and C2 is 0. Okay? So this verifies that these particular two vectors are linearly independent. Okay? Another way to see that is that if the vectors are linearly dependent, what the definition says is there exists C1 and C2 such that C1 is not 0 or C2 is not 0, right? Such that C1V1 plus C2V2 is the zero vector. All right? So suppose that, well, since at least one of the C's cannot be 0, let's say C1 is the one that's not 0. And I'm not claiming anything about C2. So I can always then write V1 is minus C2 over C1 V2. Right? This expresses in another way that in fact these two vectors are on the same line, right? Same line, and that from one you can get the other. So they contain essentially the same instructions for forming a line. They are redundant in that sense. They give the same information. Okay? Okay, so I have it here now for two vectors. But what stops me from writing the same definition for k vectors? Nothing. Just keep adding C3 and V3 and C4 and V4 and so on, right? And the same idea then follows here. You will still require that at least one of the C's is not 0 if your set is linearly dependent. And if that's the case, then you would get something like this. There might be more V's over here, but one of the V's that are dependent is always expressible as a linear combination of the other V's in that set. So if you have the other V's, it doesn't tell you anything new. Same idea. Yes? Questions? Okay. So how do you detect if you have a set of vectors? How do you check if they are linearly dependent or independent? And there are a number of theorems. So on the, what are we now on? Fourth page, I think. the slide that says how to detect linear dependence theory, right? Okay, so I have a theorem here. So you have a number k vectors in Rn. So put the vectors, all those k vectors, in one matrix as columns in the order from 1 to k. So this matrix is going to have n rows and k columns. Yes? Okay. So then the theorem is that the vectors are linearly dependent if and only if the linear system shown there, homogeneous linear system, has a non-zero solution. Okay? As we said in class on Tuesday, a homogeneous system like this always has the solution of 0. But if it has a non-zero solution, it's the same as saying, hey, one of the C's is not 0. Because what is that system? It says this, if this is a 0, 0 vector, right? In the 2 case, n equals 2. So, a much more practical method is on the right side, top of that page, that if you put k and n as before, and you make the matrix that is formed by using V1 and V2, V2, V3, Vk as columns, then the vectors are linearly independent if and only if the determinant exists and is not equal to 0. The exists is implicit here. I wrote it in an equation, right? So it better exist. So what does it imply? K for that theorem is really equal to 1 to n if that is even possible to take the determinant. Because remember, a determinant is only for a square matrix, equal number of rows and columns. So that's the practical thing. If you have, let's say, 5 vectors in R5, 5-dimensional each, right? Then you make the 5 by 5 determinant, calculate it. If it is not 0, then these 5 vectors are linearly independent, which is very, very practical. It also tells you what I have below as an immediate consequence. If we have the number of vectors k larger than the dimension of the space of these vectors, n, then the vectors are linearly dependent, necessarily. Okay? Let me illustrate it here. So I have in this picture vectors v1 and v2, and this particular set of vectors is independent. How about if I throw a third vector in? Anywhere I put it, I can always get it as a linear combination of the other two, right? Because I've already explained you can span the whole space. So the 3 here, 3 vectors in 2-dimensional space, cannot be independent. Okay? And I know it from the previous theorem because the matrix would not be square. And I would not be able to take the determinant. But then that previous theorem implies that, they cannot be independent. Right? They're independent if and only if the determinant exists and is not 0. Any questions? All right. Now, spanning sets. Now you can start with Rn and choose some subset of it. If you are able to find a collection of vectors v1 to vk in Rn such that every vector in the subspace V is a linear combination of these vectors, then we say that these vectors span big V. you can tell what feat of my high school years I'm most proud of, because it's right here as an example of spanning. It's not exactly right as an example of spanning, but what I did is when I confronted trigonometry for the first time, I was extremely annoyed because there were 100 formulas in the book, and I had to learn them all, and it was annoying. But I found that if you knew 2 of them, and you understood how you can derive the others for these 2, you can derive all of them. That was very useful. I stopped being annoyed. I figured out how trigonometry works, and that was essentially the best way to do it. Well, here you start with just enough vectors that you can generate the rest of the space, right? And it's much simpler because instead of having to write proofs, you just multiply the vectors by numbers and add them together. Okay. So the spanning set can be considered as sort of a summary of the entire subspace V, right? Okay. But for any linear space, there are multiple spanning sets, right? So for example, in this example that's already drawn on the board, V1 and V2, they are independent. We argued that already. They will span the entire R2. But V1 and V3 can do it just as well. Or as a matter of fact, the standard basis, the unit vectors, 1, 0, and 0, 1, they can also span the whole space. So that gives the idea of a basis of a linear space. You want a spanning set of vectors that spans the whole space, and you want it to contain as few vectors as possible, to be the most efficient summary of the space. That is then the definition of a basis, which is at the end of the next page. And if you go to the last page, you see just 2 slides. The first is a theorem that says, start with n, look at the basis of Rn. You can have many, but all of them will have exactly n vectors in them. And then the summary is the last theorem that connects the ideas of linear independence, spanning, basis, and determinant. Okay? So any questions? All right. So from this, what do I expect you to remember? The basic concepts and theorems like that last one. So whenever you need to verify that a set of vectors is independent, you remember, I'll put them in a matrix, look for the determinant, and see if it's not 0. Okay. Now, moving on, I want to emphasize a few things from chapters 26 and 27 in Varian's book, which is a very concise but very good summary of the math you are going to need. So the first chapter of those starts, indeed, 26 that is, on page 473, starts with some linear algebra, very condensed, much more condensed than all the slides I have given you. Then talks about quadratic forms, definite and semi-definite matrices. I, in class, gave you a little bit of an idea for that, and I have uploaded my quadratic form slides. Now, what I want to do is connect this with how we use it in economics. All right, how we use it in economics, And I will connect it by reminding you of the definitions of quadratic forms being positive definite and so on, and negative definite and semi-definite, and then jumping to the part of chapter 27 that talks about the second order conditions. Okay? So, let me remind you that the quadratic form can be written as x transpose AX on Rn. So if I have a space Rn, I can write a quadratic form on it. If I have a matrix A, which, as I explained in class, can be symmetric, such that x transpose AX is my formula. That's my quadratic form. Just as a reminder, let me indicate the dimensions of all those matrices here, right? See, a vector has multiple different manifestations. One is as a vector from physics in school, in high school. Then if it's a free-floating vector or not, here it's not free-floating. We make it stand with a basis at the origin. Then it has a manifestation as a point once you base it at the origin. And it also has a manifestation as an n by 1 column vector, right? As a matrix with n rows, however many the dimensions of the vector, n1 column. There is no particular reason, but by convention, a vector is written as a column. Just convention, doesn't matter. Okay? So then this is the dimension of this thing. So this is at the end what? When you multiply the x with the a, you get an n by 1, right? And when you multiply with that 1 by n, you get a 1 by 1. So it is indeed one dimensional. It gives you a real number. That's it. Okay? So then, we say it's positive. Well, let's do negative definite. For most of the time, we want to maximize something. So negative definite is a sufficient condition if you have a maximization to have a maximum, right? If you have no constraints and you already found the first order conditions to be 0, the derivatives to be 0. I'm not talking about that quite yet, but I'm telling you why I start by discussing negative definite quadratic forms. By the way, we can say negative definite quadratic form x transpose x, or in fact matrix A. And then the definition is if and only if for every x not equal to the 0 vector, x transpose AX is negative. Right? So if you take any vector in Rn that is not a 0 vector, and you form this quadratic form around the matrix A, you are going to get a negative number. Okay? Now, there are various ways to test a matrix to see if it's negative definite, or other things, positive definite, semi-definite, or even not definite, indefinite. The best way to understand the practical method of testing, which has to do with the leading principal minors of the matrix, is to actually use the simplest possible example of a negative definite square matrix. And this is on page 500 and 501 of the book. And he says, I love it. He says in the beginning, how can you remember all those conditions? Which leading principal minor has to be negative and which has to be positive, etc., etc., etc. And it's also counterintuitive sometimes, right? So what we're going to do is I'm going to write the 2 by 2 case, and then even the 3 by 3 case, show you the leading principal minors, and show you what signs I want them to have to ensure that the matrix is negative definite. All right? So I will do that. Let's see. I'll make some room over here. First, let's start with my matrix of A11, A12, A21, A22. Okay. How do you form a minor? You have to delete an equal number of rows and columns. A principal minor, you delete the same row and same column. If you delete the first row, you better delete the first column, right? A leading principal minor is if you delete a set of rows and columns, they must be the last ones. So this one has the leading principal minors as follows. One is the determinant of A11, where I have deleted the second row and the second column. And the second one is the determinant of the entire thing. Okay? So, having had this now on the board, here are the conditions we want to ensure this is actually an if and only if theorem. The quadratic form is negative definite if and only if this is negative and this is positive. And it is the positive part that confuses people. Right? Which is why it's really nice that Varian decided to use the most obvious of examples. So suppose I take my matrix to be the identity matrix of order 2 multiplied by -1. It looks like this, right? And if this is not negative definite, then my definition of negative definite is really strange, right? So let us actually calculate the quadratic form that corresponds to this matrix. The matrix is symmetric. The off-diagonal elements equal to each other. They're 0, in fact. All right? Okay, so the quadratic form is going to be like so. And I'll spare you the calculations, but they're very easy. You can easily check it at home. You are going to get minus x1 squared. And I prefer to put it in parentheses because sometimes a superscript means something that is not an exponent. So what I mean here is the number x1 is squared. It's raised to the second power. So it's a little clearer if you put it in parentheses. Okay? Now, it ought to be obvious that if you take any x1 and x2 here, any whatsoever, just as long as they're not both 0, this is negative. Right? Yes? Okay. So let us calculate its leading principal minors and see what they are. So I'll delete this now. I want to do it down here. Okay. So what is the determinant of the first leading principal minor, which contains the number -1? It's the number -1. Okay, it's negative. How about the determinant of the whole thing? It is, in fact, -1 times -1 minus 0 times 0, so it is +1. Right? Aha. So now you see, this is not so weird. It basically corresponds to the idea that you multiply two numbers of the same sign and you will have a positive result, no matter what the original sign was. In this case, one negative and another negative. Okay. Does that make sense? Now, if you had a maximization problem without constraints, with endogenous variables, choice variables x1 and x2, right? And you found that the first order partial derivatives were 0. So let me write it down. Maximize by choice of x1 and x2, some expression like this, where f is defined on an open set. Actually, I should put it here. So the domain of it is a set S that is open, an open subset of, oh, one more thing. I don't want trivialities. It's not the empty set. Okay, so suppose you can take first and second order derivatives of this function. It is differentiable, at least of the second order. Okay, you know what to do for a maximum. There's no constraint. You just want to maximize this. All right, no constraint. There are in economics problems like that. The typical one is profit maximization, where the firm can choose inputs to any amounts it wants without a constraint in the standard competitive profit formulation. So, mathematically, what do? We take the partial derivatives. You see he uses, yeah, okay. We take this, which is what? It is the Jacobian matrix of this. In other words, and we set it equal to 0. So each first order partial derivative is 0 at the same point. So let's actually call this point something special, right? It's a point that could be a maximum. This is the same idea, but in 2 dimensions, of taking a derivative and set it equal to 0 for a candidate for maximum point. Okay? Everybody okay? Any questions? Okay, so if that's the case, then we have the first order conditions satisfied at some point x1 star, x2 star. There may be multiple such points. We focus on one. And we ask, is this a maximum? Is this a minimum? Or is it something else? A saddle point. If a certain matrix I'm going to write down now is negative definite, then it implies that together with this, the point x1 star, x2 star is a local maximum. That is, there is a neighborhood around it over which it is really a maximum of that function, but possibly not over the entire domain of the function. Okay? So what is that? I will write the Hessian matrix. This is called the Jacobian matrix of the function f. And this is going to be the Hessian matrix of f. Oh, both of them at x star. By x star, of course, I mean the entire vector with coordinates x1 star and x2 star. Okay? So what is this then? It's getting worse and worse as I get older. Making mistakes like that. I fixed it now. Alright, I'll give you a minute to write it all down. It's in the book, but write it down, it's fine. Now, for a continuously differentiable function like that over some neighborhood, so that is, I'm assuming that first and second order derivatives of this function exist and are continuous over at least some open neighborhood of x1, x star. It is true that these are the same. This matrix is symmetric. That, by the way, has a name, and it is not the one your textbook probably told you. If you are curious, it's called Clairaut's theorem. And you can look it up and find out a little bit who Clairaut was. The funny thing is, what does your textbook say? You must have seen a name for this. If you don't remember it, that's fine, because the person who supposedly gave us this theorem doesn't seem to have left a trace in mathematics, whereas Clairaut has. And really, he should get the credit for this theorem. Okay? All right. I have a little blog post about that in dimitriosdiamantaras.me. So just go to that, my website, and put Clairaut in there and search for it. Because when I discovered it, I was like, oh, look at that. Okay. That was a digression. Back to what we're doing about the maximum. This is a 2x2 matrix in this case, right? With two choice variables. So it's like that, except the A11 is this, and so on, right? The sufficient condition for x star to be a local maximum is that, first, of course, the first order conditions must hold, and the Hessian, as you see it here, is negative definite. That's a sufficient condition. So if these are true, and this one negative definite, that implies that x star is a local maximum. And you've solved your problem, as far as finding a local maximum at least. Okay? So notice one thing that people sometimes forget. You are supposed to evaluate the Hessian at that point that you are checking, right? And it is entirely possible that you have a problem in which the first order conditions are satisfied at multiple points. And one of those points will give you a negative definite matrix here, and another will not. Okay? So you evaluate these at some particular point. That's why I added at x star here. He doesn't show this in the book. If you look at his notation, for example, on for constraint maximum, where is it? Yes, on page 493 he gives you the Hessian, but he doesn't spend all the keystrokes he would need on the computer to write it out in all its glory, all the detail. So it doesn't make it obvious. You're supposed to evaluate it at that point, which is why I'm making it probably too obvious. But nevertheless, it's not a good thing to miss. Okay, questions? Okay. What's my time? Oh, okay. Now, this is one and very useful, very, very happiness-inducing condition, because if you have the sufficient conditions, you have a local maximum, right? But there is also a set of necessary conditions. So, suppose that you found this, and then you ask yourself, what does need to be true of this Hessian so I know that I have a local maximum? The condition now is negative semi-definite, which definition I gave you, a weak inequality, right? So suppose you have a problem in your homework, and you check and you find a point here that satisfies the first order conditions, and then you check this, and one of the principal minors is in fact 0, but all the others have the right pattern of signs for negative semi-definite. Can you say for sure that you have a maximum? No. You can say, well, it satisfies the necessary conditions for a maximum. But who knows, it could be not a maximum. So this guarantees a maximum if you have the definite. Okay? It's the same idea as the second derivative being 0, right? If you find first derivative of f, only one variable. First derivative equals to 0 at some point x star. Second derivative also 0. You don't know now. Is it a minimum or a maximum? You have to keep looking. The third derivative, the fourth derivative. That you should have learned in calculus, right? That's a similar idea here. So if one of the principal minors here turns out to be 0, and the rest have the pattern that is consistent with negative semi-definite, then you say, okay, it could be a maximum. But you need to do more work to determine that if it is indeed a maximum. By the way, another tricky part is that for negative definite, you check the leading principal minors only. For semi-definite, you check all the principal minors. For that one, I refer you to the Simon and Bloom textbook. It has a really nice explanation of these conditions. I have a little thing to note here. I left it on the board on purpose. Doesn't it look asymmetric? It looks like we forgot to say that det A2 is negative. What do you think about it? Well, let's write this out. This is equal to A11, A22 minus A12 squared is positive, right? So A11, A22 is greater than A12 squared. So A11, A22 is positive because the square could never possibly be negative, right? What else do we know? We know that A11 is negative from this condition. So A22 must be negative for this product to be positive. So we have not forgotten A22 negative. It is implied by these conditions. So these conditions are nice and symmetric, even though it's not obvious. Okay? Questions? All right. The last thing then, since it's already 3:02, I want to talk about second order conditions for maximization under a constraint, where I will have that, and I will have a constraint, and I will have a bordered Hessian matrix to check. The basic idea will be similar. I will want my bordered Hessian to be negative definite, but now subject to a constraint. This one is worth some pictures. First, so let's start with a non-constrained problem. So suppose I have a function defined, let's say, on R2 to R, and it is, let's see, I actually give you a concrete example to make my point. So f of x1, x2, let us say is 1 minus x1, all of that squared, plus 1 minus x2, all of that. Okay, make it all negative. Put negatives in front of these things. And I want to maximize it. Okay? I claim that it is not difficult to see that this has a maximum, and in fact it is a global one, right at the point 1, 1. Because what is the value of the function when x1 equals 1 and x2 equals 1? It is 0, right? And if any one of the x1 or the x2 is different from 1, the function attains a negative value. So we have a global maximum at 1, 1, right? So let us draw some level sets of this function. They're going to be, in this case, circles centered at 1, 1. For fun, you can even ask Wolfram Alpha or Mathematica or MATLAB or whatever on your computer to show it to you, to show you some of them. If you are curious, I mean, this is the Euclidean distance. So what really that says, if you want to find points at a given distance from the point 1, 1, they're going to be in a circle around with radius that distance. Okay, so what happens is essentially if you were to graph this function with an axis coming out of the board as measuring the level of the function, right? Then at 0, it will be the maximum, and it will be a hill going down that way, right? And the fact that it is a hill, if I wanted to think of it with the function being measured vertically, then imagine this floor here, that origin at the corner, an x1 axis, x2 axis, and you measure the function going up. Right? And then if I'm standing at 1, 1, I'm at the maximum of the function at level 0, and anywhere below it goes down like that. Right? Mathematically, I will detect that by the fact that if I calculate the first order partial derivatives at 1, 1, they are in fact both 0. So the plane that is tangent to the graph of the function at 1, 1 is a horizontal plane. Okay, that's the first order condition. Then the second order condition would be that everywhere from that point I make a little step away, I'm actually strictly going downwards on the graph of the function. Right? That is what having a negative definite quadratic Hessian matrix at that point tells me. Okay? And this will be negative definite. You should, if you don't see it immediately, find the Hessian and check that statement. Okay, so now what? What if I have a different problem? One with a constraint. And we have seen one like that. A consumer maximizing utility by the choice of purchases of x1 and x2 given a standard linear budget constraint. Right? Okay, so I will now illustrate that case, which is more complicated than this because it has a constraint. Okay, so here's a standard story. Here's our budget. Here is the highest indifference curve that you can obtain and still be able to buy it, be on the budget. And so here's your point where you have the highest utility, right? Okay, so we know that. What I am going to ask now is, how do we geometrically see the conditions, first and second order conditions, that are indicated in the rest of chapter 27? And I will give you that, and I will let you all, including the ones watching on the video, read section 27.4 extremely, and 27.3 and 4 extremely carefully. All right? I want you, however, when you do that reading, I want you to be able to, in your mind, get some idea of what it means geometrically. Okay? That's what I'm trying to do. So the first thing is that the first order condition must hold, right? And that is that the Jacobian matrix of the Lagrange function, so we have max of x by choice of x1, x2, and we have some constraint subject to g1, x1, x2 is m. And this, of course, is the budget constraint. P1, x1 plus P2, x2 is m. But generally, it's some function. And often people write the g. And that's what he uses for the constraint function here. So, the Lagrange function, as you know, is f of x1, x2 minus lambda of g x1, x2 minus m. Right? So with that, the first order conditions are that the, let's see, calligraphical, that the derivative of the Lagrangian at the point of interest is the zero vector. Remember, that is a what vector? It's a Jacobian matrix of one function with two arguments. So it's a 1 by 2. So in fact, I didn't write that very well. Wait a minute. No, 2 by 1. No, 1 by 2. The columns become typically the variables. But all it says really, no matter how you agree to write it as a row or a column, it says the first partial derivative of the Lagrangian with respect to x1 is 0 at the point x star, and the same for the first order partial derivative of the Lagrangian with respect to x2. Must be 0 at that point also. That means actually the tangency that you see here. So the geometric manifestation of the first order condition in a problem like that is the tangency between the highest level set of your objective function, whatever you're maximizing, and of the budget, of the constraint, whatever it is. Okay? So it says these two are tangent. So this is the analog of previously without a constraint. I was at the top of the hill and the plane tangent to the whole graph of the function was horizontal, yes? Now you want to think of the tangency as being the analogous geometrical interpretation. How about the second order condition? In the second order condition, without a constraint, I was at the top of the hill, and in every possible direction I went, making a little step, I was going down. That was what the negative definite Hessian matrix meant, right? So here, I don't need to check. This is the top of my hill, but where is the hill? I'm not allowed to walk in all directions. I'm only allowed to walk in small steps along the constraint. Every other step is irrelevant. It's not allowed. That is why I am checking then for the second order condition whether the Hessian of the Lagrangian is negative definite subject to a constraint. And the constraint is the constraint of the problem. Because of how that works at the end, if you have a quadratic form and a side constraint, you get a bordered matrix where the constraint gets on the borders. It's at the end of one of my documents from Tuesday, the quadratic form document. It's also explained a little bit here. But that is why the second order condition now becomes the bordered Hessian here. And you build it like this. So the bordered Hessian at of the Lagrangian, the whole Lagrangian will go in, at the candidate point x star. So how do you build it? There are multiple ways, but here's the one he has in the book. No reason to burden you with remembering different equivalent formulations of the same thing. You do it like this. First, you need to know what is the dimension. You count how many choice variables I have. Well, 2, x1 and x2. How many constraints I have. In this case, 1. Add these two numbers. This is how many arguments your Lagrangian has, right? because the Lagrangian has the x1 argument, the x2, and the lambda for the Lagrange multiplier. So make yourself a 3 by 3 matrix. All right? And start it over the simplest possible way, 0. Now, to help us remember how to build it, I'm going to draw these little dotted lines. These are not part of the mathematical definition, but they help me at least to remember how to put it together. So, what I'm going to put here are the first order partial derivatives of the constraint with respect to x1 and x2. Evaluated at x step. Okay? Okay, so now I have filled out the one side of the border. Okay? So what did I do? I started with 0, and then I did a derivative of the constraint with respect to x1, and then with respect to x2. If you're curious as to why, I will tell you why. Because when I was an undergraduate and I was taught this, I was puzzled for a very long time about the 0. Why 0? Think of these columns as corresponding to derivatives of the following variables: lambda, x1, and x2. What I just wrote is just for you to realize something. It's not part of the mathematics, right? Labels for these columns. So, look at your constraint here. Take it the derivative of the left-hand side, or actually the whole thing. You can write the g of x, g minus m equals 0. Take the derivative with respect to lambda. Is there a lambda? No, there isn't. That's why you get 0 here. Take the derivative with respect to x1. All right, there you go. With respect to x2, there you go. All right? Now, what I'm going to put down here is the straightforward Hessian of the Lagrange function with respect to x1 and x2. So I think of it as I have the Hessian with respect to my choice variables of the Lagrangian function, and it is being bordered by something that has to do with a constraint. Okay? So, partial of L with respect to x1 squared at x star, partial of L with respect to x1 and x2, partial with respect to x1 and x2. Remember, the order doesn't matter here because this is equal to that. And this. All right? But I'm missing something. What am I going to put here? Well, that's very easy. Just put this here and put that there. Just copy it over. Now I have my bordered Hessian matrix. And in the book, you'll see the summary. What do you want its derivatives to be for the sufficient condition for a local constraint maximum? Okay? So hopefully you will always now remember how to do this. It's not really that complicated. It works if you have many variables and many constraints. It just becomes bigger and bigger and bigger. Every constraint will need a row, right? So the whole matrix becomes big. In practice, you will hardly ever bother with multiple constraints, like that. Any questions? So, this being negative definite subject to the constraint corresponds to the fact that if you walk away from x star a small distance along the constraint, You're always going down. For example, if you walk all the way here, you can see you went to a lower indifference curve. Okay? That's it. Let me stop it before it becomes an even bigger file.